As petroleum production moves to new regions with more challenging environmental conditions, producers are working to be well prepared for all occurrences. Exploration and transport will encounter sea ice, extreme weather, and months of darkness. Having well-researched, field-ready tools on hand for these conditions is in everyone's best interest. The efficient response to an oil spill begins with finding the oil. A spill that occurs under ice is especially difficult to find. Testing approaches to this task in realistic Arctic conditions is extremely difficult. The study of data gathered during recent experiments with multiple sensor systems at the Cold Regions Research and Engineering Laboratory is moving the science forward significantly.
What we've done here in the tank at Corral is, in a sense, duplicated in short term, over a few months, an entire ice season in the Arctic. But when you introduce the challenges in the Arctic of extended periods of darkness, limited visibility, and then you throw in the ice cover, it makes the whole issue of detecting an oil spill that much more challenging. And so we see it as a priority to try to identify sensors, either existing sensors or sensors that could be developed in the future to give us this capability so we could go out in all weathers and detect an oil spill no matter where it might occur in the Arctic.
Trying to detect oil that's spilled in the Arctic is really challenging because the major difference between the Arctic and somewhere else is you have the sheet of ice covering the ocean. So if you have a spill from below, that oil is now trapped beneath and you can't see it. Just detect that oil with the kind of sensors you would normally use over the open ocean has proved to be really challenging. So we're trying to look at new ways of doing it.
With funding from the 9 oil companies involved in the Arctic Response Technology Joint Industry Program, the Oil Spill Recovery Institute brought a team of scientists and engineers from 10 organizations to the Cold Regions Research and Engineering Laboratory. They were there to find out which sensors, above and below the ice, could detect oil under and within the ice.
And so we have a whole range of conditions simulated here in the tank, all the way from what could be freeze up in the Arctic, the ice growing through the winter and then melting in the spring. This project's unique, I think, because of the way it actually brings together a hugely talented multidisciplinary team of scientists, the best scientists in Europe and North America to tackle this really challenging problem. And it's giving them a chance to bring all of the sensors that they're familiar with under one roof in a controlled set of conditions so that they can compare the results. And at the end of the day, we will hopefully be able to say that certain sensors show the most promise, other sensors may not be worth following up on. We can actually see a way forward to creating an operational package, a remote sensing package that will work for detecting spills in the Arctic.
Coming up. Down there. Well, it's the first time an array of above surface and subsea sensors have been tested simultaneously under controlled conditions to gather data on oil as it's encapsulated from freeze up all the way to ice melt.
There are lots of different teams, so what really makes it unique is just the number of instruments and different approaches that we're using to find the oil under ice.
What's made this experience unique to me is dealing with both researchers from academia and from commercial business, seeing their different approaches to taking on this task. It's interesting to see how those two worlds collide and come up with some really interesting ideas that leads towards great research.
Well, this is the first time that you put all those same people in the same room at the same time, measuring the same oil thickness and ice thickness continuously. You've taken out the independent variable of all the people doing the instrumentation development, saying, okay, we have a known volume of oil, a known ice, what do you see?
Some vertical pattern, very thin one.
Well, the big advantage of Corral is that it provides an opportunity to grow a large sheet of ice under controlled conditions. And as far as I know, it's the only facility in North America that allows researchers to do this. And so I think for projects like this, since Krell, I think going back about 10 years ago now, made the policy decision that they would actually allow oil to be spilled in this basin, it's provided researchers with a wealth of testing opportunity, because not only have I been able to come in and make use of it for a lot of my own remote sensing work, but there's been many other tests done here with different types of oil spills, with herding agents, and really a lot of tremendous advances have come out of Krell opening their doors to oil spill research, and we're hoping that's going to continue in the future.
We are growing an ice sheet, and we're actually going to be growing it for a 2-month period, and then we're going to let it thaw for a month. And at different points, we're injecting oil into that ice. And then we're using sensors from above and from below to try to find that oil.
The first part of the remote sensing project that we're doing here was a technical assessment of the various commercially available and prototype sensors that are on the market today, not only above surface, but below surface as well.
So what we are doing here is a controlled experiment with a number of different isolation hoops, each a different treatment, for which we will be able to develop a matrix of the most effective sensors per the conditions for sensing oil in an Arctic environment, specifically under or on sea ice.
And we've subdivided the tank into various containment hoops. The hoops have curtains which go to various depths from 50 centimeters to a little over 100 centimeters, such that we can then grow ice within inside those containment hoops and inject oil. We're injecting the oil at various ice thickness and at various oil thicknesses.
Go at 10 hertz, Jesse.
We had a very representative Arctic sea ice. We did fluctuate the air temperature in the earlier part of the test program because we wanted creature comfort. But then we realized, okay, we just need to make it cold. So we tried to maintain minus 15 Fahrenheit continuously, and everybody who was working in the cold room had to suffer.
I hope I never really have to work in weather this cold. This kind of cold is for the brave.
From above the ice, we are using 2 types of airborne radar and a ground-penetrating radar on the ice, visible and infrared cameras, measurements of the spectral reflectance of the visible and near-infrared, and a laser fluorometer. Below the ice, there are 3 types of sonar systems, each transmitting at multiple frequencies: cameras, spectral light transmission measuring tools, and laser fluorometers. In addition to these instruments, we are collecting measurements of ice and room properties to characterize the environment we're working in. Finally, another team of scientists is taking the results of the experiments and modeling the sensor performance in field conditions.
This week we're running several different radar experiments. Some are run from above the ice and some are with our radars coupled to the ice. So it's similar to a radar that we would use to detect airplanes, for example, but we're directing it downwards into the ice, and the radar wave propagates through the air and then down into the ice, and then it's reflected from the ice-water contact underneath. Now when we have a layer of oil that's sitting under that ice that's trapped between the water and the ice layer, it changes the reflection that comes back to the surface or comes back to our detector, and we're able to use those changes to identify where the oil is located. So we've used some commercial types of radars in the past and have had good success with those when they were coupled to the ground. When they're in an elevated platform, say from a helicopter or an airplane, they tend not to work very well because they don't output enough energy. So we've developed a new radar that outputs more energy and is purpose-built for flying from a helicopter or an airplane. So what we're hoping to demonstrate primarily is that this new radar that we've built will work for this application.
So this is a 1 gigahertz ground-penetrating radar. It'll penetrate the ice, and we'll get a reflection from the salt water at the bottom. We'll also get a reflection from the oil where it's been spilled underneath. The electrical properties of the oil are different than the ice, of course, so we're going to see a different amplitude where there's oil underneath the ice, and that's what we're looking for. So right now, we're going to take part of a survey across the tank, and we're doing this weekly, and it'll be a time series of the change in properties and the ice thickness, and then also the signature of the oil as it gets encapsulated within the ice. The reflection will look a little bit different when that happens, so we're tracking that as it goes. So as I drag this sled, the odometer wheel here is keying a GPR trace every centimeter. So I'm pulling it slowly, and the wheel's triggering the GPR, and that way we get a trace every constant distance. The GPR is sending out a polarized electromagnetic wave. There's anisotropy in the ice, so it affects the GPR signal depending on which way the wave is oriented. And we found it works best to get both orientations 90 degrees apart and combine them afterwards. It's not the way we deploy the GPR in the field, but with such a controlled environment, it's a good way to get really detailed information. But one of the things we're really excited about is the FMCW radar, which could be deployed from a helicopter, say.
Well, it's really critical to be able to fly the radar as opposed to having it on the surface for safety reasons. So if there's an oil spill that's trapped under an ice floe, for example, it's very dangerous to have a team down there drilling or using a radar. So we'd like to identify where the oil is from the air as opposed to on the surface if possible.
So we're here to determine whether or not an EOIR sensor is useful in detecting oil in, under, and on ice. We have a BAE long-wave infrared camera that also has a daytime camera on board, and we're mounting on the above ice gantry. And so we have a small payload, about 250 grams, and we're looking at both visible and infrared, and for signs that we're able to detect changes underneath the ice, as well as seeing changes as they channel through.
My role is to look at how one can use sound to look at ice and oil under ice. It is unclear whether the techniques that we are trying out here today are actually going to work or not. So this is really one of the first experiments to really quantify how sound and different instruments, but my own responsibility is how the acoustic part of it, and so how these acoustic techniques can be used to detect oil under ice. Well, we have multiple different instruments. We are predominantly seeing two things. The first thing we're seeing is scattering from ice without oil is complicated, and that we need to understand that before we can hope to understand what scattering from oil under ice looks like.
So our system that's on the underwater carriage is basically a self-contained 6-channel sonar system. And the way it's rigged up is there's a bottle that has all of the electronics and power for the system, including a computer, to do some pre-processing of the data. And that bottle connects to 6 sonars that are on the carriage, and those 6 sonars are broken up into 3 sets of frequencies and at 2 different angles. And what makes these particular sonars different from a lot of more traditional technologies is they use what's called a frequency modulated chirp. So in a traditional sonar, you would send out a ping, as we call them, at one frequency. With the chirps, we scan up through the frequencies so it makes a sound like whoop.
It's an optical-based sensor. It's based on fluorescence. So we shine a light onto the oil, and the oil fluoresces, and we detect that. Well, we hope that our sensor will show that it can detect oil under ice condition and also when it's encapsulated by ice. It's unique because most of the fluorescent sensors that's out there right now are not being done at a standoff distance, so it allows you to be able to detect fluorescence at far distance compared to the present sensors that are being used now.
This high point here is the oil, and then this is not. This is the oil, and this is not.
So every time it hits the edge,
it drops. The signal drops.
And then
as soon as it hits back the oil, it picks up the intensity again.
As a geophysicist, I'm working on the physical property of sea ice and I'm working to see how the ice we grow in the tank is relatively conform to the one we can find on the natural environment like in Barrow or in Svalbard. So what I'm seeing here is an ice which grows very nicely. I'm very happy to see that because it's conform to the natural condition.
For this experiment, I'm part of the ice coring team, so we're basically taking samples of the ice, which we've been doing over the course of the experiment, to try to document the physical properties of the ice and how it's changing over time. We're trying to document both the temporal or the time evolution of the ice sheet as well as the spatial variability of the ice sheet. So we're trying to determine how the different parts of the ice have grown throughout the experiment.
One of the real fun aspects of this job is trying to get all of these very different groups working together in a very small space, particularly below the ice where you have a platform and everyone's looking for real estate. You want all the instruments really looking at the same spot underneath the ice. And of everyone saying, these are the instruments that I have, this is how big they are, and then trying to lay them out on a piece of paper originally. You know, will this instrument sit too high and then block the next instrument? You know, will this one point in a way that does something weird? That was kind of the first big lesson in how to make everyone play nice. You know, I think I counted well over 20 different acoustic systems that were all trying to operate at the same time. We had systems with light sources and systems that just measured light, you know, the passive amount of light. And so we had to make sure who got to be turned on when, who had to be turned off. Everyone figured out a way to operate so that everyone could collect data without a problem.
Well, it's been great because you have really great support here at Krell. This kind of experiment we certainly couldn't do in our lab back home. And you know, it's really interesting to see the different approaches different people are taking here and developing new collaborations with some of these people. And at the same time, you know, it's a real challenge because you've got, you know, 4 or 5 different teams trying to do things all at the same time. So trying to coordinate that is an interesting thing.
Well, it's a fantastic facility that we certainly don't have a facility like this at the Woods Hole Oceanographic Institution. The main benefit has been the interaction between the scientists and the additional information that you can get to ground truth your own measurements. So for example, I can make measurements, but if I don't have some other way to verify that those measurements are accurate, you can't be as definitive about the statements that you can make. And so having all these different scientists working on the problem together has been of great benefit.
Working with a large team at Krell has been a benefit to me personally. I've made a lot of new friends, I'll say, and a lot of new colleagues. And as a scientist, it's always good to make those contacts. That often leads to other projects, new and different projects. So it's a great benefit working with this large group here.
Just kind of naturally, you start looking over each other's shoulders. You try to understand what each other is seeing. And then you try to figure out, how can my measurement help your measurement? You know, when you read that, can you tell this aspect? Or can you tell how thick the ice is? Can you tell for sure if that's oil? Can my instrument complement your instrument so that we can make a suite of instruments that can actually work better than the individuals?
We're frozen up. Frozen up. Yeah, keep going.
I just think that this is an amazing team, amazing sensor team, amazing technical team, and I'm really proud of the work that we have done here.
This project in particular is unique and very exciting for me as a scientist because of all of the different tools that we're trying to throw at the problem to get the best platform for identifying oil spills. So if we can use acoustic techniques from under the ice and couple that with radar from above the ice and other methods that are being applied here, that would be the best and give us the best chance of identifying oil spills in the Arctic. So it's very exciting, and we're also taking all sorts of measurements that will help us learn about the ice and better understand how the radar wave is responding to the ice. So lots of interesting things here, both for our application specifically and just for the ice science in general. We're also using the data to disseminate into the general scientific literature, so we'll be writing a number of papers, hopefully collaboratively with other scientists that are working here and on our own as well.
So far, our results are showing that following an oil injection, we're able to identify oil layers under the ice and in further thicknesses based on some of the properties of the oil. And furthermore, as the oil begins to encapsulate, we're also still able to detect the presence of the oil layers.
The other thing we're learning actually with some of these sensors, especially the acoustics, is being able to understand what is happening with ice growth in new ways that we haven't really looked at before. So I think we're going to get a better understanding of both some of the processes in the ice and some of the signatures we expect from the oil. And those two things together will help us understand this problem better.
We were rather surprised to see, once we injected the oil up under the ice, even though we were using cold oil, we were having oil coming up to the surface within a couple, 3 days, which was totally unexpected by all the participants. Now, what was causing it? Was it the ice was too warm? Were there more light ends in the oil? What are the situations? But this is one of those things that we discovered.
I think this project was a really big undertaking, and I think we've executed very well. All motorized systems, refrigeration systems, they're all running to spec and keeping everything cold and at the right temperatures and growing at the correct rates, and all sensors are operational. Repairs that have had to be made have been done quickly. All sensors have performed their duty in this experiment. It's something to be proud of.
This provided that opportunity to bring in all of the potential technologies that could be used to detect oil and give them a shot. And so we were able to do this big experiment really for the first time, where you had that whole suite of sensors that are looking down from above and another whole suite of sensors looking up from below. And each one was looking at the same oil through the same thickness of ice. And so you were able to really go, okay, these are the real promising technologies. These have hope. This one can be used right now as it is. The large experiment also had another really important aspect in that you can control the environment, grow the ice at a known temperature so that you could try to hold all the different things that are normally variable in the environment. You know, you don't know how much wind you're going to get. You don't know what the temperature is going to be like. You don't know what the currents are going to be like. And all of those things may affect your instruments, but the first time you test them, you want to actually control those so that when something changes in what you see on your instrument, you can say, it is changing because I changed the thickness of the oil. It's changing because I changed the thickness of the ice. All of the sensors that we put in the tank were able to detect oil at some stage, which is great because it means that some of the sensors were really good for when the ice was warm and we were thawing things out, whereas other sensors just totally didn't work at that stage. The two that right now I would say are at the top are just a straight camera under the water, because once you put oil down, that oil is black and it makes the light go away and it doesn't come back. The other one was the ground penetrating radar, particularly the one that was coupled to the ice, so actually drug along the ice. And the nice thing about the radar, it's above the ice, and so it has that promise for being able to be put onto an aircraft, and that's where we really want to go when we're searching. And so when you combine that above ice sensors and below ice sensors, you got really a good ability to detect and locate very closely. When you look at that progression a instrument design, this is kind of that last step that you're going to want to get to before you hit the point where you say, I would like to take this out into the real world, or I know that this instrument is ready to go out into the real world. Some of the sensors are at that stage where we need to push them harder. We didn't push them hard enough during this experiment to know when they're going to fail.
Well, I think that if we're able to show that we can detect the oil that is stuck underneath sea ice reliably with one or more of the sensors we're using here, then we can move on to the next step, which is trying to integrate these into a robotic vehicle where that can move basically under its own power and autonomously under the ice. That gives us a new way of looking at oil spilled under sea ice.
Each of these sensors is capable of recording different types of data. And at the end, we're going to have information on how each of these sensors work. We're going to be able to model that data, and hopefully we'll be able to eventually fuse some of the data streams to come up with a third or fourth product that some of these sensors would not be able to provide individually, but be able to provide that as they're combined.
I think one outcome, I hope, is that many of these groups have not had an opportunity to work together in the past as a team, and I'm hoping that they'll take these relationships that they've built up through this project, and even after it's over, we'll find ways to collaborate and actually come up with new concepts for Arctic sensors that we may not have even thought about today.